Last episode, we cracked open the research paper. We learned about how the structure of the research paper is consisted, and today we're going to cook that research paper. If a research paper is like a recipe, the code, the PyTorch code, is like a kitchen. And this will significantly level up your PyTorch skill. It isn't about just like grinding tutorials. It's the process of creating a strong connection between the research paper, the original ideas, into the real code. About 7-8 years ago, they're mostly written in TensorFlow, but right at this point, most of the code is dominated by PyTorch, the deep learning code. So we're going to focus on that one. The method that I've used to cook this recipe is called a hide and seek method. I'll make a complete sense in 60 seconds and let me show you what it exactly is and how I implement it.
Today we're going to dive into the example using the attention is all you need PyTorch implementation. Attention is all you need paper was originally written in the TensorFlow, but the other contributor have written down this brilliant PyTorch code. This repository has about 2.1k fork and 9.7k star, which means that it is legit and many people have used and replicated this code. And on the left side, I have put the research paper that you can take a look. So on this hide and seek method, what I do is put the paper on the left side and put the PyTorch implementation on the right side. And the first step that you should be doing is mapping which part of the theoretical explanation is mapped into the code and how they implement it. This will not only help you to understand in depth about how the code and the model is constructed, but also significantly enhance your understanding about the PyTorch code. If you haven't watched my previous video about how to read the research paper, I really recommend reading that first and moving on here, because in that case, you'll understand the structure of the paper a lot. But the part that is mostly related to the PyTorch code is the model architecture and the training part. We're going to look into the model architecture first. Here, if you look at it, as you can see, the first section is about the encoder and the decoder. But before we dive in, when you first look at this repository, try to scroll down and read the Readme file just for a second. And mostly it explains about what the paper is about and also about the usage. This is a good guidebook to kick off with if you want to experiment and run this hub repository. And it helps the understanding about the which file in this repository is related to the which goal they want to achieve. For example, it's quite obvious, but Python train.py is about the training model and translate.py is about the testing model. So take a look at this and also mostly show about the training performance, what kind of achievements they've made. Okay, because we're interested in the transformer architecture, let's dive in. I think this author did a great job on constructing and making the naming of its variables and the file name in a very intuitive way. Let's look into the layers. So as you can see here, just looking into the import first, it used torch and a torch. And also it defined their own transformer sublayers classes that we can utilize. And it is the encoder and decoder, which we can also spot it on the left side. Let's just read briefly about a sentence. Each layer has two sublayers. The first is the multi-head self-attention mechanism. And second is position-wise fully connected feed-forward. It is composed of a stack of 6 different identical layers. And here in the encoder layer, instead of writing down the same identical layer 6 times, what they did, and also very Pythonic way of thinking, that we can reuse it across these layers. And let's see how this encoder layer is constructed. But we can see there is nn.module. There's a torch neural network.module. What is this? Why is this inside this class definition? Then now you need to have some curiosity about why we are using this module. And when we look up, I've looked up to make things faster. So here, the class torch nn.module, which is very important for you to understand, is a base class for all neural network models. Your model should also subclass this class. So as you can see in this example, and also very similar to the one we've seen in the PyTorch implementation, the first init, it defines the layers. And then in this forward layer, it creates the relationship. It connects the layers. So this is more like an ingredient part, and this is where we put our calculation inside. Okay, now that we have understanding about NN module, we go back. Here, it defined 2 different layers that they have mentioned here. Multi-head self-defense mechanism, and the other one is a fully connected feed-forward network. And let's look at the decoder layer too. It is very similar to the one above, but they have one extra layer here. So where can we find information about this? Let's see. In addition to the two sublayers in each encoder layer, the decoder inserts the third sublayer, which performs multi-head attention over the output of the encoder stack. So why is this happening? Because if you look at here, this part is encoder and this part is decoder. And there is this line that connects this encoder's output to the multi-head attention layer of the decoder layer. So it makes sense, right? So having this in mind, now you have to be curious about, how is the sublayers created? And before we go in, let's just take a quick look. An attention function can be described as a mapping a query and a set of key values pairs to an output. Query key values and outputs are all vectors. The output is computed as a weighted sum of the values. Okay, now we have understood this far, this attention mechanism. The output is computed using a weighted sum of the values. Then let's go back to multi-head attention. How is this multi-head attention created? Let's go in. So here in a multi-head attention, now before we read the details on this multi-head attention, let's look at how this is constructed. And as you can see on this left side, V, K, Q. What is this? We have read it before. It's about the values, keys, and queries. This value, key, and queries are constructed with this linear transformation. In this linear transformation, we know this n.module and one is this n.linear. This is also a very common function that you should know in PyTorch. Is about constructing the linear layer. Let's go back and look at the definition. The class torch n.linear. It applies the affine linear transformation to the incoming data, y equals x transposed a plus b. So it's basically creating like wx plus b, very common linear transformation. So here on the multi-head attention, each step is created here, and in that linear. Isn't it quite fun to see how the researchers come up with all this design and then put it into a PyTorch code? I find it quite fascinating, personally. So now we have looked into how this linear is created, but the scale.production attention is created here. And the detailed explanation is on the left side. How is this constructed? How do they use these input of Q, K, and V? Let's look into it. Okay, if you look at the scaled.production, you can see interesting functions that we haven't seen before. There is neural network dropout. If you have studied deep learning or created neural network using different TensorFlow or other libraries, you would have probably known what dropout layer is. And here there are some interesting functions used for the calculation. Torch, MapNew, transpose, transforming these tensors. And where is this base from? And then we can find that on this left side. Here, this attention function is created by using this query key torch.matmule. Torch.matmule, we can see, is a matrix product of two tensors. If you have two tensors like Q and K, this is the function that you should be using. And if you go back here, Q divided by the self.temperature and product by this K transpose. So this resembles how this attention mechanism is created, right? But here, what is self-temperature? Here, we look at this temperature. There's not much explanation over here. So if we try to read in the document and try to find the answer, that product attention is identical to our algorithm, except for the scaling factor of 1 divided by root dimensional K. Here, we can assume they use the commonly used dot product attention as defined here, but the only difference is this part. And this would probably be our self-temperature. Now we have understood how the scaled product attention is applied in this tensor, applied in this layer, and also took a look about the different functions that we haven't learned before. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected FIT4 network. And how is this FIT4 network? FFN consists of two linear transformation with a ReLU activation in between. We talked about the ReLU activation function. And where is ReLU? It's over here. And how is this constructed? This is very common, very similar to the linear equation that we have seen before. It is constructed by defining this each linear layer, and then it is conducted by performing this nested linear transformation. And here, if you look at it, there is some things that we have seen before, residual and layer normalization. So let's go back and try to look up where we have seen this. Oh, here, we employ a residual connection around each of the two sublayers, followed by layer normalization. If you have noticed here, there is something that we haven't seen before. There is 0.1. Is this a number that the author have randomly written down? It wouldn't. So let's look at where the 0.1 is. You can see here. This is the last part of training, and you can see we apply dropout to output of each sublayer, and this we use a rate of 0.1. So the author of this PyTorch implementation have followed the exact number the original authors have.
Okay, now you have basic understanding about this hide and seek method. The thing that you should be actually doing is first pick 1 or 3 papers that you're interested in. Not like 10 or 20 of them. Just 1 or 3 papers is enough. 1 or 3 papers that you're genuinely interested and can't stop thinking about how is this built, how is this created. Pick those papers. And then find the official implementation on GitHub. Make sure the code is recent because some of the search versions have a different functions. So you don't need to learn the deprecated functions. If you look at this PyTorch implementation, now you apply the hide and seek method. And there's a thing that separates people who actually get good at the PyTorch from the people who just go through these motions. So you should keep asking yourself about how and why. This line maps to this equation. Why did they choose this activation function instead of others? What does this PyTorch function or the base class mean? Why is the learning rate scheduled this way, not the other way around? How would this break if I remove this layer from this model? Be experimental, be curious, stay curious. Your questions are what teach you to think like a researcher. Your questions that you ask yourself are the things that will help you step up and make yourself differentiate from others. And this cycle, read, implement, question, and repeat, is how your intuition is built. Not from the tutorials, not from the courses. I feel like tutorials or courses are good. It helps you understand the basics. But the real intuition, it comes from yourself. It comes from the genuine curiosity. I hope you found this video helpful, and I'll come back with more learning strategies that help me to become a machine learning engineer, and also AI trends that you shouldn't be missing out. I'll try to comment as much as possible. It's quite busy lately. Apologies, and thankful for my subscribers supporting me.